Okay, so let us continue our exercises on dual space, and today we are going to finish this set of exercises. So this is the 10th one, and in this one some systems of linear equations are given, and each equation in the systems that we see here are homogeneous equations. That means the right hand side constants are all 0. So in each case we have to find the rank of the system, and also we have to find all the solutions. So let's now see the solution. So in the first system, for example, how many equations do we have? 3 equations. This is the first one, this is the second one, and that is the third one. And how many variables do we have? 4 variables we have. So let's see what the rank is in this case. Now to find the rank, we of course have to consider the vectors that we will get from the coefficients of these variables. So we start our solution like this. So this is part A. Since so what is the first vector that we will get? Its components will be 1, 2, minus 3 and 4. So the first vector is this 1, 2, minus 3 and 4, and the second vector will come from that one. So that will be 1, 3, minus 1 and 0. 0 because we do not have x4 there. And likewise the third vector comes from the third equation 6, 0, 1, 1. Since these vectors are linearly independent in F4, actually R4, but in the exercise F denotes the field of real numbers. So because they are linearly independent in F4, the rank of the system is 3, because we know that the rank is the dimension of the subspace spanned by these vectors. Since they are linearly independent, so they will span a 3-dimensional subspace. So that's why the rank is 3. And we know that when the rank is 3, then the number of linearly independent solutions, or in other words, the dimension of the solution space would be the dimension of the entire space, that is 4 minus 3. So there is only 4, let me erase this. Equal to 1 linearly independent solution to the given system. And one such solution is this. I have it with me, which you can in fact either verify or you can find your own solution. Here the values look like this. x1 is minus 26 divided by 43. x2, I do not have space. Huh? We'll come back to these things later. x2 has the value 32 divided by 43. x3 is 70 divided by 43. And x4 is 1. Now there are some things that I should address about this solution to part A, which I will do here. Okay. Now the way we started this solution, we of course had to first of all figure out the dimension of the subspace spanned by these vectors. Now in this case it turns out that these vectors are all linearly independent, but how do we know? How do I know, and how do I just simply write like this, that since they are linearly independent, so they generate or span a three-dimensional subspace of F4 or R4? The answer is that you have to actually verify, and you already know how to do that, but still let's just see that process for once. So what you do, you consider three real numbers, say A, B and C, such that this linear combination plus B times 1 3 minus 1 0 plus C times 6 0 1 1 is the zero vector in this vector space. That means okay, and then we have to check whether A, B and C all of them becomes 0 or not. So this vector equation gives rise to these four equations: A plus B plus 6C equal to 0. That is one equation. Then 2A plus 3B equal to 0. That is another equation. Then minus 3A minus B plus C equal to 0. That is another equation. And finally we have 4A plus there won't be any B here, plus C is equal to 0. Now when you try to solve these things, which you can of course do very easily, what you do is that you express C in terms of A and also B in terms of A. and substitute those expressions in one of these two equations, you will see that that gives you a equal to 0. So that is why a must be 0, and as a consequence b and c also have to be 0, and this is why they are linearly independent. So that is one thing. And the other thing is the solution to this, the solution to our original system. How do we actually go about finding the solution or the solutions, whatever they are, to a system of linear equations? For that we have methods, and I'm sure you know about some of them. In fact, this is something that we have been doing since our school days, solving systems of linear equations. But still, if we go back to the actual system that is given to us, then the actual system is this. X1 plus 2x2 minus 3x3 plus 4x4 is equal to 0. Then x1 plus 3x2 minus x3 is equal to 0, and 6x1 plus x3 plus 2x4 is equal to 0. So to solve this system, you can use the technique of eliminating variables, and for that you can use Gaussian elimination method, or you can just simply write the matrix of coefficients and then you try to reduce that matrix into row reduced echelon forms. I am not going into those things, but the point is that the techniques for solving a system of linear equations are already available. So you can apply such techniques and you will get a solution like this. And the third thing, there is one more thing. And the third thing is this. What does it mean for what does it mean when we say that there is only one linearly independent solution and one such solution is this? That just means that we have the solution space, right, which consists of all the solutions, and that is a subspace of this vector space. Now, having one linearly independent solution means that the solution space is a one-dimensional subspace of F4, and in order to specify a one-dimensional subspace, you just need to give one non-zero vector in that subspace. This is one non-zero vector, and obviously this is not going to be the only one. The other solutions, in fact all the other solutions, will be some scalar multiples of this vector. So if you find some other non-zero solution, then that itself can be used to span this one-dimensional subspace, that is the solution space. Okay, that can be done. I have just found this one, that's it. And if you want, you can put the values here. You will see that they all satisfy these three equations. So that's why we are not writing anything more. The solution space is generated by this single vector or spanned by this single vector, and that's how we get all the solutions. Okay, so now we go to part B. In part B also the situation is similar. We lost the equations. No? Let me write the equations here once more. The equations for part B are, there are only two equations, x1 plus 3x2 plus x3 is equal to 0. This is one equation, and x1 plus 4x2 plus x3 equal to 0. This is the other equation. Okay. Now here also this equation is similar. Now note that here, there we had 4 variables. So everything was happening in the 4-dimensional real space. Here we have 3 variables, so everything will happen in the 3D real space. And in this case also, the 2 vectors that we will get out of these equations in R3 or F3 will be linearly independent. Since the vectors 1, 3, 1 and 1, 4, 1 are linearly independent in F3, and here it's much easier to see that they are linearly independent. 2 vectors are linearly dependent if and only if any one of them is a scalar multiple of the other. That is not possible here, which you can see clearly from the components of the vectors. So that's why they are linearly independent in F3, and hence, so we have started it with since the rank of the system is 2. So there we cannot write R, because here also we are going to get only one vector. So there is the dimension of the total dimension of the space minus this rank equal to 1 linearly independent vector that will be there in the solution space. Or we can directly write and here it's pretty easy to find the solution just by inspecting the 2 equations. One such solution has x1 value 1, x2 value 0 and x3 value minus 1. That's it. x1 equal to 1, x2 equal to 0 and x3 equal to minus 1. So that means this vector gives us a solution for this system of equations, and the one-dimensional subspace that it spans in the 3D real space consists of all the solutions to this system of equation. So that is part B. Now we consider part C, which has the most number of equations, and also there are 5 variables. Now in this case, the vectors that we will have to consider will not be linearly independent. And in this case it goes something like this. But again, I should perhaps write down the equations first, because that way we can see what vectors we have to take. So for part C, these are the equations. The first one is just the sum of all the variables. Then the second one is small, x1 plus 2x2 is equal to 0. The third one again is long, 4x1 plus 7x2 plus x3 plus x4 plus x5 is equal to 0. And the fourth one is x2 minus x3 minus x4 minus x5 equal to 0. So in this case, the vectors that we will have are these. This comes from the first equation. From the second one, we have this. From the third one, 4, 7, 1, 1, 1. And from the fourth one, 0. Keep in mind that x1 is not there, so its coefficient is 0. 0, 1, and the others are constantly minus 1. So these vectors, it turns out that they are not linearly independent, not all of them, but rather two of them are linear combinations of the other two in this way. Since the third one, 4, 7, 1, 1, 1 is equal to the first one plus 3 times the second one. Okay. Second one means 1, 2, and the others are 0. Is that really the case? 3 plus 1, 4. 3 times 2 plus 1, 7. And these are 0, so 1, yes. This and this one, the last one, is also like that, a linear combination of the first two. And what is that? Second minus first. One minus 1, 0, 2 minus 1, 1, and the others are 0, minus 1, all of them are minus 1. Okay. And the first and second are of course linearly independent. So what is the conclusion? The conclusion is that these two vectors form a basis for the subspace that is spanned by these 4 vectors. Okay, so that's why in this case the rank is 2. Now because we are in a 5-dimensional space, 5-dimensional, that's because there are 5 variables involved and the rank is 2. So the solution space will be of dimension 5 minus 2 equal to 3. It will be a 3D subspace of R5. Hence, there are 5 minus 2 equal to 3 linearly independent solutions to the given system. And one can see that 3 such linearly independent solutions are this, or okay, if I write like this, then it will be easier to write. x1, x2, x3, x4, x5 are these, and -2, 1, 1, 0, 0. So you just slide this one, this third component. So in the next solution you write this one here and 0 here, and in the other one you write this one here. Okay, so that's just it. And you can of course verify that these are 3 linearly independent vectors in F5, the 5-dimensional real space, and they are linearly independent. And that's just it. So there is one more exercise, and this one is a little theoretical. If F and G are in V hat, in the dual space of V, that means if F and G are linear functionals on V, such that Vf equal to 0 implies Vg equal to 0. Vf is the image of the vector V under F, and this vector V is coming from the original vector space capital V, that we understand, and this 0 is the 0 scalar in the underlying field, whatever that is. Similarly, Vg is the image of V under the linear functional G. So what is given is that F and G are two linear functionals such that any vector that vanishes under F also vanishes under G. If this is the case, then prove that G itself is a scalar multiple of F for some scalar lambda in the underlying field. Okay. So the solution goes like this. So what we do in the beginning is that, because vectors getting vanished under these linear functionals, that's what we are considering, and in terms of that the hypothesis is given. So that means naturally we have to consider the kernels of these linear functionals f and g. So let nf and ng be the kernels of f and g respectively. Okay, so what is given? It's given that any vector that vanishes under F also vanishes under G. In other words, any vector in the kernel of F is also in the kernel of G. In other words, the kernel of F is a subset of the kernel of G, or a subspace, because after all these are subspaces. So the given hypothesis is then equivalent to the containment that the kernel of F is a subspace of the kernel of G. Okay, so this, it's just the same thing expressed in terms of kernels. That's it. We haven't actually done anything. But now it may or may not happen that the linear functional f is identically 0. That means it's the 0 function which maps all the vectors of V, not V hat of course, of V or the original space onto the 0 scalar. Okay, it may happen. So we have to consider that case separately. If f is equal to 0, that means f is identically 0, then what can we say about the kernel of f? Since all the vectors of capital V are being mapped by f onto the 0 scalar, so the kernel is the entire space V. Naturally, then and so Ng is also equal to V. Why? Because if Nf is V, then V is a subspace of Ng, but Ng already is a subspace of V by definition. So that's why Ng and V are equal, and which then again in turn implies that just like f, G also is identically 0 because its kernel is the entire space V. So just like if G is also going to map all the elements of V onto the 0 scalar. Which implies G is equal to 0. So in this case, the final claim of this exercise is trivially true. G is 0, F is also 0. So you can take any lambda. Say you can take lambda equal to 0 itself or 1 in anything you want. And that need not even be mentioned. So we just continue like this. So we assume that F is not identically 0. This case is over. In this case, whatever we wanted to show, that is true. Now we assume that F is non-zero. Then F will not make every vector of V vanish. There will be at least one vector whose image under F is going to be a non-zero scalar. So that vector will exist and we are now going to use that. So we are going to write like this. Then UF is not equal to 0 for some vector U in V. Now for any scalar mu, say, we have mu equal to mu times UF divided by UF. Why? Keep in mind that mu is a scalar, it's a field element, and UF is also a field element because our small f maps the vector space into the underlying field. But UF is not just any field element, it's a non-zero field element, so we can multiply and divide by that element. So this calculation is actually going on inside the field. Okay, so far there is no problem. Now this we can write as, okay, how can we write this? We want to show that this is equal to, yes, mu divided by, so what we do, we write this part separately. You will see why. Times UF. Now this product can be written like this. See if you get it. Divided by UF, U F. What do we see here inside the square brackets? Whatever is written here, this part is actually a vector in V. Why? Because we already have a vector U in V and we are multiplying that vector by the scalar mu divided by UF. Keep in mind that although U appears here also in the denominator, but it's not U, but the image of U under F, which is a scalar. So mu is a scalar divided by uf, that is a scalar. So in our field, this thing inside the round brackets is a scalar. So we are considering the scalar multiple of u by this scalar. So that is again a vector in V. On that we are applying the linear functional f. Now because the linear functional has to respect scalar multiplication, so the scalar has come outside and on u alone we have applied f, because that's what f does, right? Besides respecting vector addition, it also respects scalar multiplication, because just like any linear transformation, a linear functional is also a linear transformation. That's why we have this. Now what have we managed to show here? We have shown that any scalar in the field is the image of some vector under F, and that vector of course is coming from V. Hence, the linear functional f which maps V into f is onto, okay, it's an onto vector space homomorphism, right? So what does the fundamental theorem of vector space homomorphism or isomorphism, I forgot what the actual name is. This quotient space of V by the kernel of F should be isomorphic to the second space with which there is this onto homomorphism. It's the same for groups, rings and rings, fields, vector spaces. That theorem remains the same. So this quotient is isomorphic to F. As vector spaces, they are isomorphic. And F itself is a vector space over itself, and its dimension is 1. This we already know. Hence, the dimension of this will also be 1. This will be equal to the dimension of F. Because there is only one field involved, we are not writing a small f in the suffix here, because that denotes dimension over f. If multiple fields are involved, then we have to write that in order to avoid confusion. So this dimension will be equal to, that is equal to 1. So that means as a vector space, this quotient space is one dimensional. So a single non-zero vector here will generate or span the whole space, and that vector of course has to be non-zero. Okay, but there is a point here. Well, of course it has to be non-zero, because if you consider the zero vector, then that only generates the zero space, which is a proper subspace of this. Why? Because if this itself is the zero space, then its dimension is 0, not 1. But here we have the dimension 1. Hence, but what do the vectors in this space look like? They are cosets of this kernel in V, that is cosets given by some vector coming from V. So there exists a coset that spans this entire quotient space such that it is non-zero. That means this is not equal to the zero element, which is nf, or in other words, w is not in nf. Okay, so this is the situation now. Now where can we go from here? Now for any vector v belonging to V, you consider the coset of nf given by this vector V, that is V plus nf, and this is a vector in the quotient space which we are saying is generated by this single vector. So that means this will be a scalar multiple of this. That means this will be equal to alpha times w plus nf for some scalar alpha, that is V plus nf is equal to alpha w plus nf. Recall how we multiply a vector in a quotient space by a scalar. This is the definition of that multiplication. Or okay, now the vector V itself belongs to this coset, no doubt about that, because if you choose the zero vector which is there in nf, because it's after all a subspace, then you get V plus 0, which is V. So V belongs to the left side, so V will also belong to the right side. So that means V is equal to alpha w plus n for some vector n in the kernel of f. Okay. Now what we do? Now we calculate the G image of V, that is Vg. I think that's what, yes, that's what we have done. Now, since this is the final calculation, let me write that like this in the equation array format. Vg is equal to, we have an expression for V, so let's substitute that alpha w plus n g, because G is after all a linear transformation. So this is equal to alpha times wg plus ng. Okay. Now that is equal to alpha times wg, because ng is 0. Why? You write, since nf is contained in ng, our hypothesis expressed in terms of kernels. because we are choosing n from nf, n will also be in ng, so n will be annihilated by g as well. So we have only alpha times wg. Okay, now note one more thing, that w does not belong to nf. That means what? W is not in the kernel of f. So if we apply f to w, we are not going to get the zero scalar. We will get a non-zero scalar, a non-zero field element, which means that I can multiply and divide by wf, the image of w under f, and that's what we have done here. So what next I write is this: and this whole calculation is happening, I mean the things that you see here, the terms, they are all field elements. The final term, I mean inside we have vectors, but the final terms are all field elements. And we can in fact mention here also the reason, because why not, since w does not belong to nf. Okay, now how do we take advantage of this situation? The thing here is now this: we separate wg divided by wf, and this alpha wf we keep separately. Okay, we haven't actually done anything else, we have just clapped things together separately. Now whatever we did here, that is something vanished, we are going to bring something back here. We are going to go in the opposite direction. So wg divided by wf alpha times wf plus nf. Okay, is it okay? Yes, because n actually originally comes from nf, so just like n vanishes under g, n is going to vanish under f, so that means nf is the zero scalar, so we get this. And again, now you use the fact that just like here g is a linear transformation, so is f. That is wg divided by wf, but this is nothing but our v. And now if you look carefully, I can write this thing as v times what is this? Here we are, what you are looking at inside the square brackets is a scalar multiple of the linear functional f by this scalar. What does it mean? It means that because our f is coming from the dual space, right? So the dual space is a vector space over f again, I mean our underlying field. So if we take a scalar, this scalar in f, then we can multiply f by this scalar, and the definition of that product is precisely this, that is again going to be a linear functional, because this again will be in the dual space. Now when you apply that linear functional on a vector in the original space, so what you do is that you apply this linear functional on V, and then you multiply that scalar by this scalar. Okay, that's how this scalar multiplication in V hat is defined like that. So that's why this is equal to V times lambda f, where lambda is this Wg divided by Wf, and definitely it's a scalar. Now our V was what? Our V was any arbitrary vector from the vector space capital V. So that means the effects of G and lambda f on V are identical. They are going to give us the same scalar when applied on a given vector from capital V. So that is why as functions G and lambda f are identical. Since V belonging to V is arbitrary, we thus have G equal to lambda f, and that's what we wanted to show. So this completes the solution, and it completes this set of exercises also on dual spaces. In the next video, we are going to start inner product spaces. That is the inner product or dot product of vectors that we already know from physics or from our vector analysis in the 3D space, that is generalized in some special types of vector spaces via some functions called inner products, which behave like ordinary dot product that we are well accustomed to. Okay, so that we will see, and we will see how far inner product spaces mimic our ordinary 3D space, and in fact how far that general definition of inner product matches with the ordinary inner product in terms of their properties. Okay, so that's just it for tonight. So I end things here, and the next upload is this coming Friday. So this Friday let's do calculus. So with that I wrap things up. So see you on Friday with calculus. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.